Hi everyone, welcome back. This is going to be our final episode in the run of thermodynamics videos, where we discuss Gibbs energy and equilibrium. We've talked about how we can relate entropy and the enthalpy and either entering or leaving a system to the amount of work that can be done by that system, or the amount of work that has to be done to that system in order for the reaction to carry forward. So in this one, we're going to look a little bit more subtly at the idea of Gibbs energy as a measurement of spontaneity, how much work we can get out of it, and exactly when we can stop getting work out of it. So once the system reaches back to equilibrium. So just as a quick reminder, what do we mean by equilibrium? So this is the, excuse me, we're looking at, let's just have our generic chemical reaction. So A and B as reactants turning into C and D products. We would draw the arrow this way in recognition that there's going to be a certain balance, especially once we reach this equilibrium point. As much reactant goes over to become product, some product comes back to reactant, and there's going to be some ratio that becomes consistent over time. So if you remember, if we start, say, with only A and B, or let's just focus on A, I guess, to start with, we have an amount of A, and this will be in time, and that's going to go down towards zero, but it may not reach it. And let's say that C is going to be building up, and it's going to come up at the same time, and it's also going to reach some sort of level or percentage that's still in the solution, concentration in the solution. And that ratio is going to remain stable over time. So that's the period that we're looking at when we talk about equilibrium. And so we want to think about that ratio. We'll assign it a variable, K, as we've seen so many times before. And this is the concentration of the products divided by the concentration of the reactants, or the ratio of the products to the reactants. And that's at equilibrium. So this is our equilibrium constant. Equilibrium constant. Okay. You might also remember that this is also true, but anytime outside of equilibrium, this ratio is called Q. So it's equal to exactly the same thing, but it would be at any kind of period in here. So as it's still changing. So this would be kind of the K at equilibrium, and Q anytime before that. Okay. So for spontaneous reactions, so again, how are we going to tie this idea of equilibrium back to Gibbs energy? Well, if we have not yet reached equilibrium, if this reaction is going to proceed, we have some ratio there that continues to change, and we're in this Q region, but let's take it all the way to equilibrium. For spontaneous reactions, we already know that the change in Gibbs energy is going to be less than zero. So a negative Gibbs energy means that it's a spontaneous reaction, which also means that the reaction is going to proceed forward, right, as written. So for A and B going to C and D, it will continue in the direction as it's written. What else do we have here? So Q in this case, so the ratio between the products and the reactants at this moment is still going to be less than K, which indicates to us that the ratio of, say, Q to the equilibrium constant itself is going to be less than 1. Q is going to go towards 1 as it goes towards K, which also implies that ln of Q over K is going to be less than 0. Okay. For non-spontaneous reactions, or now we're starting to think about where A and B isn't going to result in C and D. In fact, we're going to have it spontaneous in the opposite direction. So for this one, delta G, or the change in Gibbs energy, is going to be greater than 0, and the reaction would proceed in the reverse spontaneously. And so what does that tell us? That tells us that the ratio between the products and the reactants is higher than equilibrium. So Q is now going to be greater than K. So Q over K is now greater than 1. And ln of Q over K is positive. Okay, so now we have these two relationships where we say, okay, where Gibbs is less than 0, this ln of the reaction quotient by the equilibrium constant is less than 0, so we see they're the same. And here, for non-spontaneous reactions, if Gibbs energy is greater than 0, then the same thing here, so ln of Q over K is also greater than 0. And of course, at equilibrium, so when everything is settled down, delta G equals 0. There's going to be no change in the Gibbs energy, or no work is available to be done. Q is now equal to K, which tells us that Q over K is equal to 1, and ln of Q over K is equal to 0. Okay, so again, we see that this value, this ln of Q over K, is going to track with Gibbs energy all throughout its domain. Okay. So what can we do with that? Well, let's try to relate that quantity between delta G and now ln of Q over K. We know that they're related somehow. It's just a matter of what constants are we going to put in front of it in order for it to be equal to each other and not just proportional to each other. So, so let's say that delta G, and we'll give it the standard here, is equal to RT. So this is the gas constant, 8.314 joules per mole Kelvin, multiplied by the temperature, times ln of K, or Q over K. Okay, so this is going to be our proportionality constant between these two values. So this is also equal to RT ln of Q minus RT ln K. And there's something we can do with this, because Q at standard conditions, so this is why we threw this little, we want to talk about delta G under standard conditions. When we're looking at standard conditions, all of the concentrations for everything is at 1, right? Concentration for our little model system there would have been A is 1 molar, B is 1 molar, C is 1 molar, and D is 1 molar. So Q is now going to just be 1 over 1. This whole thing goes to 0. And the only thing we're left with under our standard conditions is that delta G standard equals negative RT ln of K, which is our equilibrium constant. And what else can we say there? Generalizing a little bit, if we just want to say delta G under any conditions is now going to be equal to, so now Q can be any value, probably not just a series of 1s, but it's going to be delta G standard plus, and now we're just going to add back in that term, RT ln Q. Okay, so these are our two equations that are going to be quite helpful in the next portion and moving forward. When we want to think about, okay, either the maximum amount of work we can get out of a system under standard conditions, because this is something we can look up in a book, and so is the equilibrium constant. So we can relate those directly back and forth together. Or we can say, okay, under any other concentration of our reactants, if we take this tabulated value and this something that we can measure, now we can generate or even kind of impose on the system, if we want to talk about setting it up. If we were looking from an engineering point of view and saying, okay, we're going to maintain a concentration of these different values so that we can extract a certain amount of work from the system, how much work we'll be able to get from it given these starting conditions. So these are the two equations that are going to be quite useful, so make sure that you have them at hand. And we can start off. Actually, let's just run through this whole series of examples. And I think it's a pretty good demonstration of what we're talking about here. So the example is the oxidation of SO2 is too slow at 298 Kelvin to be useful in the manufacture of sulfuric acid. So the manufacture of sulfuric acid, we've got kind of the starting over here. So 2SO2 plus oxygen into 2SO3 as a precursor into sulfuric acid. Okay, so we're saying it's too slow at 298 to be useful. Too slow, again, doesn't mean that it's not favored or it's not spontaneous. It just, again, we're talking about the kinetics of the reaction as opposed to the thermodynamics of the reaction. Okay, so it's run at high temperature. So first question is calculate the K, so the equilibrium constant, at 298 and at 973 Kelvin. Okay, so at 25 degrees Celsius and at 700 degrees Celsius. And it gives us the standard Gibbs energy at these two values. Okay, so this one's not going to be too bad. We can start with our delta G standard. So we've got this equals negative RT ln K. We want to calculate K, so let's just do some algebra on this. So K is equal to e to the negative delta G over RT. And those values we have. So at 298, we have K is equal to e to the negative, where is it now? Okay. To the negative 141, 600 joules per mole. And transform it into joules instead of keeping it in kilojoules, because again, you know that we're going to use 8.314 joules per mole Kelvin for our gas constant, and then the temperature is 298 Kelvin. Okay, and our K value here is 6.6 times 10 to the 24, an extremely high number. All this says is that the products are very heavily favored, thermodynamically speaking. Again, even though at equilibrium, it's going to be essentially all product with very little reactant left over, the time it takes to get to that end state is not specified anywhere, just to say that it's too slow. It could be years to get to equilibrium. So, okay, let's try it again at 973 Kelvin. So start out with the same equation, and all right, now we have negative 12, 120 joules per mole per 8.314, that's a 3 joules per mole Kelvin. Multiplied by 973 Kelvin. Okay. And the answer there is just 4.5. So the ratio is a lot smaller. If you were looking at this, you're going to have a significant amount of reactant left in the batch, which may not even be a problem, because you can just, as long as you can extract that product, it's going to keep driving towards establishing that ratio of 4.5 SO3 per, I guess SO3 squared, per oxygen times the SO2 squared. Okay, so that actually takes us to the next question. What else can we see here? Okay, so we also have K values. It's good. Okay, both of the delta G values are negative, so it's a spontaneous reaction in both cases, which of course is what you would want. If you push it up to the very limit, that means that look, the Gibbs energy is going down as we get higher in temperature. It will reach a temperature at which it becomes zero. And anything past that, of course, it's going to be a non-spontaneous reaction. You're going to end up pushing all the way back the other way, where this K value is going to start becoming, well, less than 1, right? Okay, so let's keep going with this question. So now we're talking about actual containers filled with measurable pressures. So this is where we want to start thinking about how does Q enter the picture. So remember, we have Q are under is a ratio or at pressures or concentrations of the reaction as it proceeds that are anything outside of equilibrium. There's no reason to believe that these are going to be the equilibrium values. It's just that it's what it's actually at. So now we're going to want to start thinking about this other equation that we had where it's delta G for any scenario. It's going to be delta G standard plus RT log Q. Okay, let's see. Which direction, if any, will the reaction proceed to reach equilibrium at each temperature? Okay, so we don't actually need this one yet. All we're asking here is going back up to our general discussion about spontaneous reactions. We want to say if Q is greater than K, then it's non-spontaneous. If Q is less than K, it is spontaneous, and it's going to be driving towards K. So let's look for our K values here. And our K values are this very, very high value, and 4.5. So if we get it less than those values, then we know that it's going to be driving forward. Okay. So let's see what it has to say. So Q is what we really want to calculate because we want to compare these values to their K values. So Q is going to be the pressure of the SO3 squared. Again, check back for that squared because of the stoichiometric values. Divided by the partial pressure of the SO2 squared multiplied by the partial pressure of oxygen. And we can fill in all these values. So we have 0.100 squared over 0.500 squared by 0.01 with some zeros. Can't quite see it. Not squared. And if you do the math on that, we get 4. Okay. So under these conditions, we don't really need to take temperature in there because when we compare it directly with either the 298 or the 973, we're going to be comparing it at the same temperature. So let's just look at this Q value for the 2Ks. So running back up to our equilibrium values, is 4 less than 6.6 times 10 to the 24? Yes. Therefore, it's going to be running spontaneously. Or the reaction is going to proceed in the forward direction is what it's asking. And is 4 less than 4.5? Again, yes. So this is still spontaneous. It's still going to run in the forward direction, which again should make sense because the delta G in both of these cases is negative, meaning that it's spontaneous in that direction. Okay, and here's the one that we were really driving at before. So calculate delta G for the system in part B at each temperature. Okay, so let's just start filling this out. So we have delta G at 298 is going to be, we have the delta G standard at 298, so this was negative 141.6 kilojoules per mole. Just keep track of your units. We may want to, well, we'll certainly want to change that around because we're not going to, or at least I'm not going to put the R value into kilojoules. Plus 8.314 joules per mole Kelvin times 298 is our temperature. And ln of Q, and Q is 4.00. Okay. So remembering that this is actually 141,600 joules per mole plus the second term, we end up with negative 138.2 kilojoules per mole. Okay, and doing the same thing, delta G for 973. Now we have negative 12.12 kilojoules per mole. And okay, still the same gas constant, 8.314 joules per mole Kelvin at 973. And ln is the same Q, so we still have 0 or 4.00. Okay, so negative 12,120 plus this term at the back gives us a grand total of negative 0.9 kilojoules per mole. Okay, so delta G still negative, which is good because that's in keeping with everything else that we've seen so far. And now under these conditions, we can say, okay, it's still negative. It doesn't give us a lot more wiggle room, right? So under those pressures, those partial pressures, as they were made in that container, it gets us very close to 0 delta G. Going any higher than that, or bringing up any more positive, or much more positive, is going to run the risk of entering into where it's non-spontaneous and it starts driving back towards the product. So what does this matter for our process? Well, we're not really trying to extract work out of this process. We want the product. So the fact that there's less work that the system can accomplish at this point is kind of immaterial. It doesn't really matter for us. Why do we want to go with that higher pressure or that higher temperature? Remember, it was to overcome the slow speed of the reaction at the lower temperature. So even though we have a smaller ratio of product to reactant and we have less delta G in the end, presumably we're going to have it at a much more faster rate that's going to allow it to be economical in a practical sense. As chemical engineering students, this is something that you'd be thinking about. How are we going to make sure that we can put out enough product that the factory still makes sense? So where did all this extra energy go? Really, one way you can think about it is something has to drive that extra rate, right? If this is going faster, the system is doing more work to get that done more quickly, okay? So we're getting the result that we want just by moving around the pressure in this case we're not really talking about, but the temperature, the concentration of the reactants, all of these thermodynamic principles coming into play and allowing the business in this case, but really the engineer behind it, to come to a conclusion that can work for everybody. Okay, so that's going to wrap up everything that we need you to know for thermodynamics. There's a lot more questions in the book, and of course you can find more example problems in our Google Drive folder. So thank you as usual for watching. I hope you got something out of it, and I will see you next time.